I think that we should probably get started. I was waiting on a fourth to possibly show up. If you're the fourth, will you please come up here? So I'm Megan Hamilton. I'm actually a PhD student from Utah State University, and I've been asked to come in and help with moderating our long paper track presentation today. So this is Juan, but he goes by, is it Ari? Okay. And so what will happen is we're going to give them 12 minutes for presentation, and then the 3 minutes will be open, like, for questions and comments and things from the audience. Okay? All right. So do you need help? One moment, we'll work with technology, and then we'll start.
It's okay. We're good? Good afternoon, everyone. My name is Ari Torralba. I'm a third-year PhD student in the Teaching and Learning and STEM Education program at the University of Miami. I am presenting my paper, A Mixed Methods Approach to Investigating Proportional Reasoning Understanding in Maker-Based Integrative STEM Projects. That is a mouthful. This paper reports findings from a pilot implementation of a maker-based STEAM curriculum in a formal educational setting. This work is part of a larger project focused on maker-based STEAM education for minoritized students. As many of you may know, the maker movement has expanded quite rapidly in the past several years, and it continues to grow within K-12 education. Through the adoption of maker spaces as formal or informal educational learning environments, schools are bringing making to their students as a new yet familiar way of learning. These maker spaces and the making activities that take place in the physical and social environments are helping develop makers of different kinds and levels of expertise. Over the past several years, we have also seen a big push for STEAM learning in K-12 education. Among several things, this push has focused on the meaningful integration of STEAM content, experiential learning, and of course, standards alignment. My work specifically focuses on the intersection of these two, the maker education and STEAM education. And that positions my work in something that I call maker-based STEAM education. The theoretical foundations of this study are rooted in the work of Halverson and Sheridan, Martinez and Stager, and Blickstein. Individually and collectively, their works have positioned the maker movement within well-established educational learning theories. Their conceptualizations offer us a better understanding of the term maker education. With these conceptualizations, I am able to use a social constructionist lens to better understand student learning as they engage in maker-based activities. The purpose of my study are to contribute to the literature on STEM learning through making in formal educational settings. For my study, which is a pilot, I developed a STEM curriculum that is, excuse me, this kind of went the wrong way. I took a shift to mathematics learning through making, and I situated this learning as an elective course, as an individual elective course. For this course, I developed a curriculum, which I call iTeams, and it stands for Integrating Technology, Engineering, Arts, Math, and Science. It is both standards-based, but also maker-focused. I asked the following questions. Does participating in a maker-based integrated STEAM project impact students' understanding of grade-level proportional reasoning standards? And how are students demonstrating their understanding of grade-level proportional reasoning standards in their final products and artifacts. To answer these questions, I took a conversion mixed methods approach, as described by Creswell and Plano-Clark. This approach basically takes both quantitative and qualitative data to understand one specific construct. I used the quantitative data, oh, perfect, you can see it better over there, to use pre and post assessment data to see whether there were changes in performance, and also the qualitative data to stay true to the data, to the students' constructions, which were the artifacts that we're making, and also their presentations. So this was divided into 6 stages. The first one was to develop the questions that I was trying to ask, both with the qualitative and quantitative aspect, then collect the quantitative data, and use that data to form groups for the qualitative stage. And then for the third stage, I implemented the post-assessment for the quantitative part, and then collected the presentations and the student artifacts. I then analyzed the data separately, then merged them, and at the end, interpreted the results. The context for this study were the following. The participants were 37th grade students from a K-8 public school. 47% of them were white, 33% Hispanic, and 13% African American. 17% of them received free and reduced lunch. The study took place in the 7th grade classroom, where I built a maker wall, which is a modified maker space. Here, the math and science teachers, as well as the English language arts and the social studies teachers, were involved in the teaching. I also brought in a curator from the Lowe Museum of Art to teach the students the basics of art, and also brought in 2 engineering students from the College of Engineering at UM to teach the students how to use Arduinos. The intervention was obviously the curriculum that I developed, and we focused specifically on the geometric moving art, which was a project that lasted about 6 weeks. And the goal of the project was to design, build, and present a team-made geometric moving art piece. The results were the following. For the quantitative part, I ran a pair samples t-test, and that showed no significance. I was intrigued by that result, so I disaggregated the data to better understand what happened there. And I did the following. I basically regrouped all the individual scores and then grouped them according to the groups that I used for the qualitative part. So at the end, you see the team names, and those are the names that I used for each of the products that I collected. For the qualitative part, I analyzed the oral and final products using a coding framework. 2 of the codes were the following: proportional reasoning, proportional relationships, and this one looked at whether students understood the connection between a 2D sketch and the actual product, and then proportional computation, which is the ability of students to be able to compute calculations for the main product using a scale factor. I also used levels of proficiency for this analysis, where I used the letters below expectations, developing, knowledgeable, or advanced, depending on at what level they were explaining these understandings. So this is basically what I collected at the end. Here are some of the things that the kids created. The first picture is the actual 2D sketch, and the second picture is what they deliver at the end. As you notice, most of the sketches there are very detailed in terms of their measurements and all the movements and progressions. The final product, is a lot better constructed, and the ones that don't have as much information, they're a little shaky. The best ones of these, I would say, were the MMGs, the rainbow, and the glitter. And from the last 2, I have the following quotes from them in terms of their work and how they applied mathematics to it. The first one, basically, I asked them, how was mathematics applied into what you created? And here, the students were trying to explain that the final product doesn't actually look like the way that they designed it, and it's not because they didn't understand it. So their intention was to have 2 inches between each of the shapes that they had, but because they had tying problems, that didn't quite happen. In fact, this team had a lot of issues with construction. So the product, which was, oh, Jesus, where'd it go? This one right here. It kept falling so many times that they had to redo it almost every time we met. So the problem was not so much that they didn't understand the connection between the sketch and the final product. It was something to do with construction. Then the glitter team, which is the last one at the bottom, and that one to me looks very symmetrical. And I told the students that that's what I thought. So they answer with the following quote. It's like, it's funny that you said it's very symmetrical, but we never actually used a ruler to construct that. We used the design to guide us because the construction was so hard in terms of tying that it became a problem. So they circumvented this entire problem and took a conceptual approach to proportionality between the 2D sketch and the final product. So without using both, I would have easily just dismissed it and said, well, according to the quantitative results, this was not good. But using the pre and post assessment data and also the oral presentations and the final products, I'm able to get a deeper understanding of what really happened there. And to understand, to get multiple perspectives on what students are actually learning and how they're demonstrating what they're learning. So the use of the two also gives me explanatory power and also triangulation. So to answer the questions, did they impact their learning? I would argue that yes. Although the pre and post assessment data says no, the use of the other data allows me to understand that they do, but they did it in different ways, which answers the second question. They demonstrate this learning not by an assessment of whether they get the answers wrong or right, but by explaining the entire process and by showing through their constructions their learning, which is basically the nature of constructionist theory. So the implications of this work, obviously, it's a mixed methodology. I believe that it gives you both the benefits of quantitative measurements and also allows us to stay true to the constructionist principles of making, which allows us to engage in multimodal analysis. And for practice, I think this work can also provide guidance on development and implementation of maker-based team projects. Lately, I've been working with a lot of teachers on how to bring this to the classrooms. And most of the times, they ask us, the standards, what about the standards? We need to focus on the standards. And I think by starting backwards, by thinking with an end in mind, what is it that we want the kids to learn? And then figuring out how to build those things and what specific parts of a makerspace they need, it might be easier for them to bring this to the classrooms. The problem I've also noticed is that people want to build these spaces and spend so much money in them, and they don't know what to do with them. And by starting with the curriculum first, I think it kind of minimizes the problem of the cost and also the problem of what to do in these spaces. The limitations of this is obviously the sample. It was not very diverse in terms of ethnicity, SES, gender, and language. And also the instruments, I think I need to strengthen the pre and post assessments and also be more specific with the rubric. I'd like to lastly acknowledge my second advisor, Dr. Ji Shen. He wasn't involved in the collection of data analysis or writing of the paper, but he did guide me throughout the whole process and also encouraged me to take on this whole project on my own. So that's all I got for you. Thank you. Oh, perfect. That was under 12 minutes. I did well.
Okay, so that opens us up for questions. Do we have any questions from the audience?
There's a question right there.
You said that it sounded like the kids had trouble constructing. How did you come up with that method of constructing the mobiles or the art piece? And would you, in terms of collecting data on sort of success, how did that impact just the technical difficulty that they experienced?
So they were using fishing line to create those things. And those are really hard to use. And that was their choice. They also had strings of like thread and different ones, but they all wanted this fishing line because it's clear, and they would look like it was floating. So the ones with the many spheres, they had the most issues because they were using pins to connect all the spheres, and they were just not staying together. Even with super glue, it just wasn't working. So that became a problem. Actually, the sixth team that we had, they never finished because of those issues. They kept breaking and breaking and breaking, and they did not have the perseverance that the one with a bunch of spheres did. Those kids literally came back every time, and they would break, and they would just go back to it, put it back together, all patiently, like, okay, it didn't break. It's all put it back together. So I think this is a problem, obviously, because I cannot make many conclusions because the construction problem was well ingrained in it. So. But for the next iteration, which will start in the fall, I'm using completely different materials for that, definitely. Any other questions? Yes.
Yeah, I was just wondering, because the contractions kept breaking, do you find that it impacted the students' desire to continue with the project?
She wants you to repeat the question.
Do you mean into the mic? Into the mic.
Oh, me?
Yeah.
Oh, sorry. So she's asking me if basically the fact that it was breaking, that it affected students' ability to persist, essentially, right? Yes. For the last project, the last team that didn't finish, they were over it. It was at the end of the semester. They were just done with it. It was an elective course. They already did what I asked them to do, which was the 2D sketch, and they tried to actually finish it. However, for the team, the one with the spheres, I think they were so invested in it, and they noticed that it was going to break no matter what, that he actually helped them be okay with the fact that it was breaking. So the perseverance here, I think it kind of grew on that side. They just wanted to get it done. So it could be both. Any other questions? Yes.
I'm curious, considering that maker education is often looking for ways for student agency and student direction, and this model seems very much to fit into a more conventional teacher-directed form of education. Is that something that you could see developing an assessment model that included more student agency?
Yes, I actually saw one of the posters that was discussing assessment, and I noticed how they were including the students in how to assess their own learnings. I think that would be a good thing for me to include in the next iteration, to get their input on how would you assess somebody else's project. I was looking specifically only at the proportional reasoning. There's many ways that I can go about this study, but for the purposes of this one, I was looking at whether or not they could understand or demonstrate proportionality through that. And in a sense, the projects are very constricted, and that's because the problems of schooling, that I was being asked by the school to also focus on the standards, not just on making for making. So this is a way for me to do both. Yes. Good question. So she asked me basically how I dealt with students' composition within the teams, and how I dealt with students who were more engaged than others. So I used the pre-assessment data to understand the levels of performance on proportional reasoning, so that I could build teams that were diverse in performance. So I had low, high, and mid-level performance in each team, and they were about 5 to 6 students per team. And because I had already worked with these kids prior to this study, I knew them all. So I knew how to get them engaged, and I knew with which students they felt more comfortable working with. And the dynamics, I think that matters. When you know the kids, you know who to pair them with. Any more questions? Oh, sorry.
Any last questions?
Thank you so much.
Thank you, Juan. Can I use that? Can I use this?
Yes. Can I just go?
Is this your timer? Sorry. Is this yours? Are you keeping time? Oh.
I'll give you a thumbs up when it's at 12. Or do you want to go morning?
Sure.
I give you 1 minute warning before it's 12.
Sure, thank you. Oh, that's not. Hi. I'm short. Okay, hi. So my name is Deb Louie, and I'm here on behalf of a larger research team, some of whom are setting up a Biomaker workshop upstairs, some of whom are sitting in the audience, to present our paper, A Revaluation of How We Think About Making, Examining Assembly Practices and Artifact Imagination in Biomaking. So, hopefully, because of this morning's presentation, when I say making, you don't just think about these contexts, but these are generally the typical contexts that people are talking about when they talk about making, you know, whether it's crafts materials, electronic materials, or digital materials. But this paper focuses on making with biology. And that's actually significant, not only because you can make cool stuff, as you've heard this morning and this afternoon, but that it actually changes the paradigm of how people generally relate to biological content, especially when they're novices. So when you think about, you know, back to your early days of learning biology, you sort of engage in these practices of observation and description. But making with biology is different because it asks you to think about designing and creating with living materials. So it kind of draws from fields that already exist, like synthetic biology and bioengineering. And these fields really focus on how you manipulate biological systems that exist in the world, whether that's a cell or a mini ecosystem, for like a new kind of output that you can use for design purpose. So this might be something like, if you've heard of it, but like leather that you grow in the lab that doesn't need to come from a cow, or mushroom-based building bricks or other kinds of organic materials that you can use for construction in the real world. So in terms of bringing novices into biomaking, you know, we heard some interesting sort of discussions about it today. There are sort of materials you can use like yogurt or kombucha, but if you want to do sort of synthetic biology on a genetic, which involves genetics, you know, there's kind of a limited accessibility of the materials and tools you might need. There are websites and there's like the processes of CRISPR, but you need to be in the know. It's not like the same as going to Radio Shack and getting a robotics kit. Additionally, you kind of need underlying biology knowledge. You know, you have to know about microbes. You have to know that they need to be fed and what their life cycles are. You need to know about genetics a bit in order to really participate and be able to tinker in like those ways that we talk about as meaningful. Finally, dealing with living organisms is highly unpredictable. You have millions of cells you're dealing with, and you want to sort of corral them to do what you want them to do, but just like us, they're very unpredictable. So trying to get them to do things when you're a novice is really difficult unless you're very precise and you actually know what you're doing. So this is all to say that I'm not saying that you can't do biomaking with novices, but that there are certain challenges that relate to the inherent properties of that practice itself. Especially when you think about the qualities of maker activities that we generally talk about as being, meaningful making. So I think we all agree that when you have products that people create in making, you think about personalization. And what do you need for personalization? You know, you need easy to customize elements. You want a product that kids can actually situate in their everyday context so they can show them off to their friends and their parents. Also, we talk about the processes of making, and we talk about tinkering as kind of a gold standard where people are experimenting with different materials. But here, when you see tinkering within making, you often see discrete, easy to engage parts. You see tangible feedback from processes that kids are working on. And then also the processes themselves have to be reversible. So once a kid does something, you want them to have the opportunity to redo it if it's like not to their liking. Like that's the power of tinkering. So the desired goal of both having personalized products and tinkering as a process is that you promote student agency. So what about biomaking? So in biomaking, you can have these things, but I mentioned before those kinds of like limitations. It's a little bit harder to personalize your products because the elements are not as easy to customize. Also, sometimes you're creating things in the lab and they seem very removed from everyday context, so people don't maybe have the inclinations to sort of be like, oh, look, Mom, I have this Petri dish with this like cool color. It's not the same as like having a pillow that you can like put on your bedspread at home. Additionally, tinkering, as I mentioned before, is a lot more difficult because there's living organisms. You need to know something about biology first. But also there's just like other constraints, like the parts are liquid and they're non-discrete, so once you put things together, it's really, you can't take them apart. The feedback is highly delayed. It's not like when you're coding, it's instantaneous. Here you might have to wait 24 hours for growth or more. And also the processes are not reversible. So once you replicate cells, so there's a million more cells, you can't like undo that process. If it's not to your liking, you kind of have to throw that away and start all over again, which might take, as I said, 24 hours or more. So I feel like I just made a case of why biomaking could not be the ground for quality maker activities. However, the purpose of our paper is to really revalue other practices which are very prevalent within biomaking that you don't normally see promoted in like the atmospheres where we talk about maker activities. So these two qualities are assembly and imagination. So how do I define these terms? So assembly we define as following pre-prescribed step-by-step processes. Oftentimes, we talk about these processes in a kind of a derogatory way in opposition to tinkering. However, I think as you all know, if you make things, it's pretty prevalent when you're trying to learn how to make things, you have to sort of follow steps and repeat over time to become better. It's key to developing mastery over time. We see these not only in people becoming better at lab work, when you think about the typical stuff that you do in lab when you're in high school, but also in the master-apprentice dynamic where you have to repeat things step by step over long periods of time. So it's not just that assembly is bad making, it's that it's a part of making inherently. In terms of imagination, I'm sure you all are saying, imagination is definitely within the maker movement. But what I'm kind of talking about is an imagination that's inspired by something that happens in a biofabrication context called speculative design. So it happens in a lot of design contexts. So this is the quote I'm going to read to help you understand what I mean by that, which is, when most people think about design, most believe it is about problem solving, but there are other possibilities for design, and one is to use it as a means of speculating how things could be. So the important thing to note here is how things could be. So this is about imagining a future using these kinds of technologies. And for our purposes, for novices, it's being able to move beyond one's own limits of what you can do. So even if kids are not yet at that level where they can really make the things that they're dreaming up, it's important to give them the opportunity to think about that and to actually apply this to socially and ethically relevant contexts for solutions for the future. So yeah, these two things you'll see talked about a lot when you see biomaking sort of happening in the field. And we want to think about how these two practices can occur for novices in a classroom. So the research question that I have today is, how can assembly and imagination in biomaking support characteristics of maker learning? So you'll hear a little bit later on, and if you go to the workshop that we actually have right after this upstairs with Justice, who's over there, we have designed multiple biomaker or curricula that we have implemented. And this is just one, and it's called Biosensor Workshop. It took place over 7 to 9 days in a STEM elective class. The classroom teacher who actually led that is also sitting over there, so you can ask her questions later. And our participants were high school juniors and seniors, so it's 2 different classes. And the workshop was really interesting because, as I said before, we had assembly and we had imagination. So we had 2 phases to this class. In the first phase, which lasted 2.5 days, they assembled a physical biomaker product. So you might have heard about this all throughout the conference and wondered, what does that actually look like in the classroom? And this is what it looks like. So in step 1, they went through the process of genetic transformation. And all that is that they actually added designed DNA to put into existing bacteria to make it have a new outcome. So here, the new outcome was we wanted this E. coli that doesn't respond to the sugar arabinose to do something. So the DNA that was put into there was designed to sort of get new bacteria that's produced to sense sugar in the environment and then to produce glowing proteins, to basically fluoresce. And then they incubated the cells overnight for replication. And then in step 2, for those new cells, they built a physical device to hold this bacteria in a solution of mystery water. So they followed pre-prescribed steps to create this contraption, and then they actually suspended it in this beaker that either had water that did have arabinose or water that didn't. And then on the 3rd day, they actually used a UV light to check whether or not there were glowing proteins in that beaker, which would therefore sort of clue them into the fact that there was sugar there. And so this is a biosensor. So they did this over the course of 2.5 days. In the second phase, they went into that imagination activity that I mentioned before, which was imagining a hypothetical prototype. So they were in small groups of 3 to 4 people. They were assigned a real-world pollution site where there was issues with toxic chemicals. And then based on what they had built, they were asked to design a biosensor that would actually sense this toxic pollutant and actually tell people out in the world, there's bad stuff here, and the levels are too high. And then they were asked to create a design board at the end that they would share with their peers. So now moving on to findings. So how did these 2 things help us think about maker education in potentially different ways? How did it support maker education in the way that we talk about it? So the affordances of the assembly phase was, not surprisingly, that it gave them hands-on experience with biomaking tools and materials. So Milo says, I enjoyed the specifics of messing around with the bacteria and all that. And other students mentioned this as well, saying that they enjoyed sort of manipulating bacteria to make it do what you wanted it to do. And even though this kind of seems kind of simple because all maker activities are hands-on, this is actually not trivial here because, as I said before, it's not easy to have access to these materials on an everyday basis. You're not going to have kids doing genetic transformations like in their after-school programs. I mean, you might if it's a biomaking after-school program, but generally you would not. So this was something that the kids sort of liked and sort of said like, wow, I actually got to touch and deal with these things. Additionally, because it was an assembly phase, they had step-by-step instructions. They had like a really easy point of entry into this thing that might have otherwise seemed kind of scary to them. So we had step-by-step instructions, as I mentioned before, and like lab technicians on hand so that they could actually easily sort of step into this process and feel like they were doing something. And then finally, we provided a proof of concept. Biomaking is like, as you probably could tell from all these different things, like kind of out there. So you tell people all this and it sounds like science fiction, but this allows them to see like, actually this can happen. You can make bacteria glow or fluoresce. And this is like sort of a powerful aspect of this phase. Some challenges, not surprisingly, are that they sort of lacked student agency. A lot of them said they were just following directions. And also, that's a picture of like 2 of the projects from 2 of the groups, and you can see they look identical because they follow the same exact instructions. So they kind of lacked opportunities for any kind of personalization. However, the exact opposite happened during the imagination phase, where we saw that they actually created all different kinds of products and hypothetical ideas. So they were allowed to explore really diverse ideas. So the buoy and the bionic fish was an idea that involved a flotation device, which was like inspired by the thing that they had made. But then they also added this robotics element in addition to sort of the biosensing that we were talking about. Other groups like talked about genetically modifying plants or fish or seaweed, which is also a plant, sorry. So the thing about it was that because they were imagining, they were able to sort of like imagine all these different kinds of contexts that they wouldn't have otherwise done in the assembly phase. Also, they had greater agency in shaping their own experience. Some of them were more interested in the design phase. Some of them were more interested in the sort of background research phase, and like that was really powerful to them as well. And then also they were able to consider biomaking within a wider real-world context, which they really appreciated. So some of them weren't even aware of the fact that there were EPA Superfund sites and that there was like problems with toxic pollution. So they said that they appreciated learning about that, and not only that they could use biomaking to address those problems in the future. Not surprisingly, there were challenges. Some kids were upset that they didn't actually get to make the thing that they had proposed. And other ones, sort of said, I wish you could have had more hands-on experience here. It would have helped me understand things better. A student, Josie, that's a pseudonym, she says, let's go to the lab and make real stuff. Like, that's what this made me want to do. All right, so in terms of the discussion, there's like 2 areas we kind of want to talk about. First, sorry, I'll be really quick, is like this helped us reconceptualize how to design biomaker activities for the future. We found that assembly and imagination could be the basis for meaningful maker experiences. But another thing that we might consider doing for the future is like, it would be useful to add some tinkering in. It's not that tinkering is all bad, but that, you can't just do it 100% maybe in this context, but you can consider maybe, not having everyone create exactly the same projects, giving them opportunities to sort of make new kinds of contraptions. And even when they're imagining their, projects, have them sort of experiment with like the buoy that they might be talking about. And so this is like another thing that's near and dear to me. Like, how can what we do with biomaking help you as maker designers who don't do biomaking, like, design your activities? So I think that like this shows us 2 particular lessons. First, that assembly is and can be a quality maker experience. It can promote that. It shouldn't be thought in opposition to tinkering, but in continuum with them. And it's also key for introducing the context that might be new or novel or scary. And that we should sort of, start to think about the ways in which we can like hack assembly practices within our maker activities. Additionally, imagination sort of allowed students to engage with existing socio-scientific issues. So like when you think about robotics, you might have them do a robot on, in their classroom, which is a great thing, but by having them do an imagination phase, they could think about like the future of AI. They could think about data privacy. So this is one way you can get them to engage with these larger issues and then foreground a longer trajectory of engagement. So I'm already out of time, but we have a lot of other efforts that people in the audience who are on this research team work on. You already heard about some kids from the Biodesign Challenge. There's someone in our research team who's actually doing research on students who are also doing that. We have 2 other curricula, including BioCakes, which we'll have a short workshop on Right after this session, there is an incubation machine that's going to be released very soon. And if you want to know more about this, you can either email me and I can connect you to the right people, or you can ask me right now, or you can find the people that I point to in the audience for that. Thank you.
So this time for questions.
Yeah, I think that's...
This time for questions, I'll try to locate you in the audience so that the people from a distance can actually hear the questions this time. So if you have a question, will you raise your hand for me? Maybe you can meet me in the middle, I don't know.
Thanks. My question was about the idea of sustainability, and question, I guess, is do you think that the idea of sustainability is automatically built into biomaking? I'm thinking, for example, in Australia, where we had unintended consequences when we introduced rabbits, and all of a sudden we've done something to the environment that had long-lasting consequences. We invented plastic 50, 60 years ago, and we've done something to the environment that had unintended consequences. So as we approach kind of a new kind of revolution in something, how can we kind of learn from the mistakes of the past? Is that baked in already in terms of what you've seen? Or should we be thinking in terms of, should we put a greater emphasis in terms of ethics in biomaking, in terms of sustainability, and being cautious that if someone makes something, they don't just flush it down the sink and forget about it and have unintended consequences? So I was wondering if you had thoughts about that.
Yeah, I think there's people who are like right around that I think could answer that right now. I just want to say quickly that I don't think it's inherent within a biomaker activity. We did bake it in. The person who helped design the curriculum is actually right there, Justice. I think you could answer that question better than I. Can you give him the mic?
Thank you, Deb. I think it's an incredible question to consider, like what happens to the organisms that we're genetically modifying and having kids use, and what are the potential negative impacts it could have in the environment. But one thing I want to emphasize is that these things are happening already. And so if we're not teaching kids about those processes, we're going to have a generation of folks who can't contend with them happening right before their very eyes. And so while a lot of people are really concerned about like what this might look like if we take it on as a community and teach kids how to do it, one thing we have to realize, it's already happening. And so I think our duty is to teach kids these practices and these potential consequences early on so they can contend with it in the future.
I had a quick question. Thanks for the talk. I really enjoyed it. And one of the ideas that you brought up is how you integrate speculative design into these types of environments. And I was wondering if you could speak a little bit more about how you created kind of the scaffolding for them to speculate on what could be, as well as talk a little bit more about why you think there was kind of this disconnect between their speculative designs and the imagining phase towards actually getting that integrated into the assembly phase when they're creating with the biomaterials.
So first, how it was scaffolded. I could answer this, or you could answer this, Justice, or Sheri could answer this, because all three people were involved in that creation, and they're sitting in the audience. But it should actually be mentioned that before we did this curriculum, we did this other same curriculum with them, BioLogo, and we talked specifically about sustainability and having sustainable solutions to real-world problems. So like that already, I think, set the scene for thinking like, oh yeah, how can we make like first of all, like in a product design kind of orientation. And actually, I think Sheri can answer this because you created that design board, which was, I think, was an amazing scaffold. She is, do you mind, Sheri? It's an amazing scaffold where she specifically asked them to fill out particular parts of the design, such as like what they would sense, what pollutant would be sensed, what could be used for this. Sorry, I mean, it's a design board, and I feel like that was a really great scaffold. And sorry,
I think because we had done some e-textile stuff together before, and we were talking about how what we were doing in manipulating biology was very similar to programming. So I think that them doing the actual transforming the bacteria and things like that was a little, because they were used to getting more immediate responses. So that was a little bit difficult. But while we were talking about it, I think we changed that from when we were talking about it. We talked about it when they were learning about it as if it were, this is a sensor and you have an actuator and you have all these things in this, so you have to think about it very logically. So then I think when they went to the design board, it made sense because we had that scaffolding there, and then they thought about their design from that perspective. And then that made it, I think it made it a lot easier. And then they felt like they had control over it, so they had that agency to be creative, but they had a nice sort of base to start from.
Yeah, and then now, as I remember, actually, they had a whole entire activity in the beginning where they actually took apart a smoke detector so they could understand the parts of like, oh, this is how a sensor would work to alarm humans in the world. Then you also had done your e-textiles one in another curriculum, and then here we're making a bio version of this. So they already had like these things in their mind that they could pull from.
Okay, thank you. Wonderful questions.
Good afternoon. I'm here to present a research study that we conducted in the summer of 2017. Okay, I think I'm feeling very short out here. I can't see anything. Okay. This is the outcome of a game design workshop, a game making workshop at a very large public library in the Southwest. We had only teens as participants, 8 teens. We divided them into 2 teams. And the very big focus of our workshop was to generally see so given that we ask teens to design games that are set up in a science context, what science do they learn? So we had hoped to see a very different kind of learning than we actually saw. So a little bit about our workshop. We followed the day school design thinking model. We described this process to the teens over one entire week, with the general understanding that when they begin to make something, making is equal to learning, as all of the maker research and maker pedagogy kind of states. We set the context of the game narrative as water pollution. We described a lot of water-related problems that the Southwest faces. Our first big question was very general, was just to see what science do they learn. These are some pictures that give you a general sense of the workshop. Sorry, I had to adjust the brightness and the contrast not to reveal the participants' faces. But it was very informal. We worked mostly through a very detailed design process, but did not give them too much about the problem of water pollution. That was their job to find out, do the research, ask us questions, interview people, things like that. So we began by asking them, so what do you like about games? What kind of games do you like? What elements of game design do you like? And if you were given a chance to design this game about water pollution, what kind of games would you design? So we found out that most popular games were Settlers of Catan, games that kind of integrated really intense gameplay, but also a complicated board and cards, tremendous amount of confusion, very competitive games. And the kids created 2 different games, both set in the same context. So one is called Ludo Club. As you can see, it has a very Settlers of Catan-like board. There are 6 biomes which are linked to a central biome. There are action cards, event cards, good event cards, both bad event cards, and there are pieces of plastic. And the plastic somehow because of these global events and local events, the plastic enters the water biomes, they can flow, and all of this can be controlled using the action cards. And the outcome is that one biome or all the biomes, or what's the level of pollution that happens there. And based off of these kind of effects, there are outcomes in each of these biomes. The second game is called Save the Farm or Not, because it's set in a farm that explores the kind of intentions that industrialists have and environmentalists have and farm owners have. And cards are played. This is an exclusive card game, and there's a central board that keeps count of the track of pollution, what's more, what's less. Animals die or all your plants die, and there are combative events that can take place. Very complicated game. Anyway, so based on what we found, we actually had to completely change our research question. As if someone asked us, so what would you say what a science learning while game design set in a science context looks like? We would say that the first big questions that we faced was, okay, how is this science? Or what aspect of science learning can we connect this to? The first, attractive aspect of this is that we wanted to go towards science content. And then we realized that, yes, they are learning a lot of content. Throughout these two games, the biggest aspects that they can see is how much they have learned about pollution. But we wanted to go a little bit more specific and move away from the science content and think about what are the processes that they have learned that are very much there in nature, but they are not explicitly taught about in school, or they could not have learned about this through their research. And we asked them to confirm that. But this was an outcome of the process of making the game, of building the design. And here's what we found. So our theoretical framework was, of course, based on constructionism, that learning takes place while you're making something, taking things apart, putting them back, trying to build something new in a social context, and that's how it becomes meaningful. About the science learning, we found out that learning to think in terms of systems was the biggest outcome of this game design process. We try to think about that. There's a lot of research that's now available about learning in systems, but what does this clarify? That they're not just learning to think about system as in how would we define a system? So there's a system, like a game is also a system, but it's pretty defined. There are very defined rules. There are cards, there are boards, people are playing it. Unless and until you factor in intentionality of the players, a game is a pretty simple system. Now, water pollution or polluted water is a completely different aspect altogether. It's a very complex system. We do not know how many factors are important here, what's affecting those factors in turn, what is flowing from where, what kind of pollutants, do the pollutants interact with each other, what. So the level of system thinking is varied. Of course, that was our biggest learning too, and we drew data for this presentation mostly from one presentation. We played the games that the teens created over a period of time. We played it with them, we played it without them to understand their learning process. We divided our findings into three big areas. One was learning about games as system, because we talked so much about game design and what aspects of game they like, what they don't, what makes them interesting, that they really learned about. So what makes a game interesting? And the answer, of course, lay in the design, that there are aspects of game design that bring people together in a way that help you sort of manipulate or make use of the game context in certain ways, and that's how a game acts as a very interesting system. The second aspect was the learning about water and polluted water as a system, and here's where the science aspect plays in. Our biggest evidence are in these categories, like learning in levels, like what do you mean by polluted water? Well, pollutants in water come from different places. Or once your water is ruined, you really cannot say like how it is ruined. It's just bad water. I mean, there are certain attributes of it, but it's going to act as one entity. Feedback loops, like once water is polluted, how does it affect life in water, life outside of water that comes in contact with the water? How does it worsen it further? And then this aspect of learning from game design, that there are aspects of games, the game narrative and water pollution, that they actually tried to, how you impose one design onto another design, and that's how you realize in your effort in aligning these two designs that, hey, these cannot actually be aligned that well. They are very different things. Their understanding of what constitutes a system, what constitutes a complex system, and what happens when we try to design a system to mimic another one, and that there are several factors that control each unique system, and it actually cannot be done. The biggest implications that we found was that we really do not teach children how to think in terms of, I mean, whatever we do affects a system. That kind of, I guess, because we try to teach so much content in school, science content in school, is that these larger aspects of thinking scientifically is not really catered to in school. But this is something that can be done exceptionally when through a design process, especially while designing a game. We felt that it led to a change in perspective among our teens. We thought making games was a very good preparation for future learning, because it opened up doors to so many questions, and questions that would intrigue them for days and help them set themselves up as better learners in the future. Systems thinking, of course, model-based reasoning, because the games ultimately became models of polluted water flowing through a much larger system. Our final point was that the narrative of the game and the design process are both, and the design of the game are both essentially very important to the game. I mean, if one doesn't work, the other doesn't work as well. That's all. Yeah, I have time for a few questions, huh?
Hi, I have just a really quick question for you on systems thinking. I'm trying to teach some scientific systems as a beta site science class over in Hong Kong. And how much, and I think it's complex systems, it's getting students to understand subsystems within systems. It's quite difficult. How much did your students know about the interconnectedness of systems and the importance of that before you started this workshop?
That's actually a very good question. So when we began talking to students about, not students, teens, about polluted water as such, so they did not mention too much to us. They said, yeah, water is polluted. We asked them, so how does it become polluted? And there's stuff from the industry that enters water. There's plastic bottles being thrown into water that causes pollution. But we really did not hear them talking about how exactly that affects the water, or how exactly does it affect the water downstream or upstream, or when it runs into the ocean or things like that. Whereas when they designed the game, all of these aspects of systems thinking that we talk about were evident in the game, but not in the talk That is before the process. Now, they did some research that they independently carried out during the process, but our understanding is that in their effort to make a game interesting, they kept on introducing more game elements. And if there is a game element representing something, it has to do something within the game. And that's when those kind of connections were realized. It's not like they didn't know, it's just that they didn't know that this is exactly the way in which it works. Ultimately, in fact, both the games, they became so complicated, they had to cut down on those interactions that they were designing on the concept, mostly because they didn't know how they would act. Does that make sense?
Okay, I think we have time for one more question. No takers. Okay. All right. Thank you. So our fourth presenter, I don't believe, is here today. So I think we're going to end the session, but great work going on, and there were some great presentations today with great questions. So have a good, I believe it's on to workshops now. So have fun.